the call. We got Coldint coming up on stage. Let's do it. Hoorah, let people fill in. 49, 253. This is an exciting call. Here we go, people. Some news from OTF side of the world. Assalamu alaikum to you, Zion, as well. Commit reveal is on DevNet right now. CR3 is on DevNet. We're just still testing a couple things right now. Should be on testnet by the end of the week, and looking for probably a Monday launch for CR3. It's exciting. We'll talk a little bit about that on the call at the end, or with you guys. You guys have some questions for us. I'll also be in Neural IPS doing a talk at Neural IPS next week, Tuesday, 8:30 a.m. at the conference, if you happen to be there. So if you'd like to come and visit, see me chat about Bittensor, and basically take credit for every single thing that all of the amazing miners and validators and subnet owners have done over the last little while. If you can suffer through that, yeah, feel free to come to that conference if you have a ticket. It's hard to get a conference at Neural IPS. Corporate cons, yeah, exactly. Happy $100,000 Bitcoin. We were right. We were early. Some updates from people in the community. Exciting news from BitAds. BitAds has been making strides selling advertisement space. Celium is paying our validator for the compute. All of the pods are unavailable on Celium, which is, I guess, a good thing. Kind of annoying. Been wanting to use that. Those are the two things that I saw last week. But today we're going to be chatting with the Coldint team. 29. Some of the most intelligent people that I've ever met in my entire life. I often get on calls with them and feel intimidated. So I'm very anxious being up here with the both of you. Maybe we can start with a bit of introduction. Coldint has been around for a while, like since the 1990s. Is that right? Can you guys give us a bit of a history? Or are you?
I will speak with echo probably, but so yeah, we met in the 1990s, 1999 to be precise, and then we started studying physics together, and then we both went our own ways. RWH went into research, did a PhD in quantum physics, and went on with that. And I went on to become a software developer after studying law as well. And then I joined a company in online assessments, sold it, started a new company in IoT, and now went into Bittensor 9 months ago. I'm planning to do that for the time to come. And I hope RWH has found his microphone.
Great. Thank you very much. Thanks for the great introduction also. And yeah, you gave most of the backstory already, I guess. We never did much with AI, but until a year ago when things really started to get big, and we got interested, and we have Bittensor to thank for it also in a large part. So, and we made some slides that we would like to share. So thanks for having us on stage. And yeah, so we wanted to start the story, back in the early 90s when we started discovering computers. And we saw this interesting creature appear. And it was, made by nerds in their basement or kids in their attic room. And it also, in a large part, motivated us to start coding. And of course, this Linux was surrounded by lots of big companies that made operating systems, but really the open source philosophy and the collaboration between these different people made something big. And we kind of see a similar vibe now with Bittensor also, where it's a collection of nerds and smart people coming together to try to make something similar in AI space. And of course, there are lots of big companies doing great things as well, but we think that Bittensor can really play a big role in teaching many different people about AI, develop interesting tools, and hopefully some useful applications as well. And this is really the thing that made us come towards AI and Bittensor about a year ago. So we see it as our goal to help a little bit to make Bittensor the Linux of AI. So what do we need to get that going? I think for Bittensor to really become the Linux of AI, we need to scale to many subnets. We also need to scale to bigger models, because bigger models are smarter than smaller models and will get much more interesting work done. If we want to scale to many subnets, we need efficient validators, because if everyone has to have a machine for every validator with a very expensive GPU, it will not scale very well. Also, we need a stable validator code base, because if you do updates, it becomes a system management nightmare if the validator code doesn't run well or has problems with updates. We also think we need to scale to bigger models, and there we see again that it would be helpful to have efficient validators that treat these big models, efficiently, so that you don't need super large amount of compute. I also think we should do some smart training, because we want to do it efficiently. So we started out as miners in Bittensor, and then at some point there was a great opportunity to register a subnet at a not too large scope. So we happened to be able to do that. And we started the Coldint network. So it's collaborative, distributed, incentivized training network. And our main problem statement is how can we efficiently train and validate large models in the Bittensor network? And we think the most important ingredients are gradually growing models and developing optimized tools. This can be both in the validator code base for us and in training for the miners. And we see it as an important factor to build a miner and developer community around this subnet. And in general, we should boost the open source AI development. Our core motto of our subnet is to train smarter, not harder. And based on this motto, we started thinking, how do we want to train big models? Well, you can, if you have one model size, let's say 7 billion parameters, you want to train a 14 billion parameter model, you can start from scratch, but it's kind of a waste of all the work that you've done before. So what we are thinking about is how can you do that in a gradual way and extend the models that you have at one point and grow them gradually so that you get bigger models. It's also motivated that this is not a pipe dream by this paper that we show here, where some researchers trained a 101 billion parameter model in several stages, where they extended the model gradually. So this is really possible, and we think we should investigate this further so that we can efficiently train bigger models. Now, of course, there are always lots of technical issues if you train or if you evaluate models. And one of the first problems you run into is that big models don't fit on a small GPU. So let's say you have this nice llama model and you try to plug it into a GPU. At some point, it will not fit. So what you can do then is you can distribute your model over several different GPUs. And whether this is in inference or in training, in both cases, it's necessary. In training, of course, it's necessary much earlier with smaller models. And you can divide your model over different GPUs in many different ways. So I will describe one method here, but of course, there are many different methods that could work as well. So let's say you cut the llama in 3 parts, and you plug the 3 parts into different GPUs. So, for example, every GPU would hold 10 layers of the model, and the model has 30 layers in total. So you kind of split the model in space. Now let's say you have this, and you how does a timeline look when you evaluate a model? So you start with GPU 0, you evaluate the first 10 layers of the model, and then what you get after that is the hidden state, and they describe the complete state that is the communication between the different model layers. So you can pass these hidden states to the next part of the model in GPU 1, make that one do its computational work, and then pass the hidden states to the top 10 layers in this model. What you get out then is the loss values. So how well the model predicts the next token, because typically we're working with LLMs here. So this is just the inference part, but if you want to do training, you can do that in this configuration as well. So you can do the backward passes on the 10 layers on the top and get the gradients of the loss versus the hidden states and pass it back to one level lower, the 10 middle layers. And then you do that again to the 10 layers on the bottom, and then all the GPUs, all of the 3 GPUs can update their model parameters at the end of this. And this is called pipeline parallelism. And we like it a lot because it's a kind of intuitive way to distribute your model over several GPUs. And it's very memory efficient. And it works really well for us. And this is not something we invented. You can read all about this in the paper I cite here. And what you have to do if you do this in training, you have to send lots of samples or sequences into the model after each other. And in that way, you can really use the GPUs efficiently. You will only have the hole here on the bottom, which is called the bubble. And in the end, if you do this well, you can use the GPU power quite efficiently, because it's hard when models become bigger to use all of the computational powers of the GPU. And this is one way to distribute a model over several GPUs. Now, when we are validating, we can do a different trick. So similar to the pipeline parallelism, where we split the model in space, we can split the model in time. So let's say we have only one GPU, and we first load the 10 first layers of a Llama model. We can compute the hidden states and then plug them on the same GPU onto the middle part of the Llama model, and then again for the final part. And still, we will get the loss of that. And of course, this costs something, because you have to save the hidden states in between evaluating the different layers, and you have to unload the first part of the model and then load a new part of the model. So there is some cost, but if you evaluate the things in this way, you can load a very big model on a relatively small GPU. So it's a small change because we modified the Llama model code in transformers, and it's not that many lines, but it has a big impact, because in this way we can validate a 10 billion parameter model on a 24 gigabyte RTX 4090 GPU. It's no problem. And in fact, this is our validator hardware of choice. You know, it's cheap, relatively cheap, and it will do the job just fine. And in this way, it's a pretty efficient way to evaluate the model.
A question.
Yeah.
When it comes to things like residual connections in models, does this way of breaking down the design still work, right? Or does it do the residual connections require caching more state and it's still within reason?
Which residual connections do you mean?
I'm referring to in the design you're presenting right now, in pipeline parallelism, you take the hidden state, you feed it to the next section of the model, which is loaded onto the same GPU. But with a residual connection, you'd need to actually maintain the hidden state from the first layer and pass it to the one of the final layers of the design. This, have you taken a look at models that are highly making large use of residual connections, and has that affected the performance?
We have not, but I think in the base in the Llama models, this doesn't really exist, and I think the reason is that it's also harder. It's always more computationally hard to use this other state, right? Because the attention mechanism in general and the structure of the model is such that you can split it in a nice way. So the layer is completely self-contained, and that's the nice part about it. So you don't have to have state from earlier layers. Anything that is, all the state from the earlier layers is completely encoded into the hidden states. So you only have to pass hidden states between layers. And it's actually quite, the nice thing about this pipeline parallelism is that the hidden states are actually relatively compact. So it's somewhat easier to share between the different GPUs than sending the whole gradient of a whole model. It's quite compact. So as I mentioned, it's a relatively small change, but of course we have to write some wrapper around it to use it in a simple and transparent way in transformers. But in essence, it's a small change that has a big impact, and we really see it as a helpful improvement to, especially for a validator where latency of evaluating a sample is not so crucial. It's okay if it takes a minute for a batch of 100 samples. That's not a problem. But in a real life application where you talk to ChatGPT, it's of course not so convenient. Now,
if you don't mind, Ardewesh, if I interject and give some of the audience more context about what you're actually describing, because and unless of course you are just about to get to this, but we're speaking specifically about Subnet 29 and the bottleneck on Subnet 29 being the evaluation of extremely large models and how you fit that into small validators effectively, right? When you're talking about maybe going up to 100 billion parameter model.
Yeah, we don't want people to rent ginormous GPUs, right? So you'll have to split the model in some way, and we think that if you split it in this way, you can do it on smaller GPUs. Yeah.
Exactly, and this is the major bottleneck in both of the, well, there's now a couple more, but the larger training subnets on Bittensor being 9 and 29, where how do we blow the lid off the size of the model that the miners are allowed to train without suffering from validators not being able to evaluate them at all, right? That's the core problem that you're talking about here. It's not so much about training, because Subnet 9 and 29 leave the training and the efficiencies of training and the co-location of servers and the interconnect and whatever you are particularly using to speed up your training process. That's all left on the mining side. So the real bottleneck is how do you just evaluate these models? And
Yeah.
I think that, yeah, so anyways, that's just a bit of context here for the audience.
Yeah, no, exactly. And there are more, I guess there are a few more training subnets. And now I'll switch gears and talk about another feature of these training subnets. And that's how do they validate the models? And so for 9 and 29, there is a pool of models that remains in the pool and remains a set of interesting models. And the models are evaluated in rounds. And every round, we pick a certain number of samples. So for example, in this case, 800 samples, and we make a matrix. So for every model and every sample, we compute the loss. So in total, for this example, it'll cost you 800 samples times 6 models times n floating point operations, where n is the number of floating point operations per evaluation. Now, how does this look in time? So in time, you will evaluate several, in this case, 6 different models. All the losses are produced, put in a table, and in our subnet, we pick for every sample, we pick the best model, and the best model gets 1 win. So every sample will result in 1 win for one of the models. And in the end, you get a ranking based on this score. And what typically happens is that the next step is to throw all these expensive losses into the bit bucket, and they disappear forever. Now, if we scale things up, so we have more models, the model size goes times 2. The number of samples goes times 10, because if you pick more samples, it will allow you to make a more fine-grained estimate of the relative performance of the model. But this will mean the compute might go times 100. And all of a sudden, it becomes a very good question if it's a good idea to throw all these computed losses in the bit bucket. And we think it's not a great idea. So we had this feeling from the start when we began the subnet that we really wanted to improve this the way the validation was done so that it's less costly. What we do is we take a pool on each validator of about 20,000 random samples, and per eval we evaluate 1,500 samples. And it will result in a big matrix. For every model and every sample, there is potentially a loss value, but there are also empty spots, as you can see here. And we use this as an enormous cache. So every time we can compute a ranking, an emission based on this big matrix, big table, and we keep the losses. And if a model, so if of course a model is bad, we only have to compute 1 round of samples, so 1,500 samples, and then we can ditch the model. And if a new model appears, then we don't have to recompute losses for all the models that remain in the pool. So basically, it's just a big cache, and we don't recompute all the losses every time. And this is an enormous advantage, because if a new model appears, you only have to compute losses on a small set of new samples that belong to that model and fill in a few entries in the table. And then you can directly compare it with all the other models that you already had the loss values for. So it's an efficient use of time on the GPUs. Is that clear, or are there any questions about this?
Let me see if I can repeat it back to you. Because you maintain the loss for each model on all of the different samples in this massive cache, when you want to compare a new model that comes online into the subnet, you simply need to pick and choose from this large cache which samples to evaluate that model on, because you don't need to reevaluate every single model. You can just evaluate this new model on these samples and then go look in the cache to see how the previous models performed. So you effectively have it's a massive optimization in terms of the speed of the evaluation process. Whereas I think the original version of SN9 was take the top models, take a random sample of pages, evaluate them all on those new pages. So it was 10, 20, 100 times slower than what you're describing right now.
Yeah, and it feels kind of stupid or superfluous to pick new samples for the models that you keep in the pool. It's fine to reuse the old samples. There's no real need to pick new samples every round. There is, of course, the danger that someone learns these samples. So to prevent this, we slowly rotate the pool of samples in time. So every few hours, the validator loads, I think, 500 new samples. So that it does slowly rotate, but still most of the samples that we use are in the cache typically. So it's very, very helpful, I think. Yes, so there's one other thing we wanted to discuss. So these were some technical innovations that we did in the subnet, and I think they also could be applied to other subnets, by the way. I think that every subnet that compares models, this is a strategy that you can use to be more efficient on the compute. So what about subnet quality? So subnet quality is limited by the competition. So I always feel that the competition quality cannot exceed the efforts of players 1 and number 2. So player 1 delivers the value by producing in this case, the very, very best model. But player 2 ensures that player 1 has to keep performing. And we strongly believe that player 2 should get incentive to keep competing and to keep pushing the first player to improve its model. And we kind of say it's helpful in competitions to have a silver medal. And I think probably it's also helpful to have a bronze medal so that you keep on pushing each other. You need competition. And the other analogy that we sometimes use is if you have to run a marathon and you're on your own, you can run the marathon at 1 mile per hour and you will finish just fine. But it's not the best performance that you can get. You need competition from other players to get the best level of performance from the subnet. Of course, how well the competition does is also bounded by the incentive mechanism. So the validator algorithm should really reward the goal that you want to achieve. So it should reward a good model and not, if there's a bug in your validator, it will totally put the incentive somewhere else and not align with the goal of producing a good model. And also the validator efficiency is also very important because the compute limits determine how well you can actually, in this case, compare the different models. If you can only evaluate one sample, it will not be a very good competition. So we believe that to get the subnet quality high, we really have to have a good algorithm to compare models and also do it efficiently. And these are the 3 things that we really focused on when building this subnet. And we already wrote about it in our blog posts, really when we started the subnet, that these were the goals that we wanted to achieve. Now we also have the collaborative and distributed in the name of our subnet. So what do we have on that front? So we have a somewhat flat incentive distribution in our subnets. You can see the leaderboard on the lower right here, and there are several different players that produce models. It's quite an active community, I think, and several different players, and yeah, the remarks are split between them. And
Why
we
is it
really see it as, sorry?
RWH, why is this mechanism flat, as you just described it? I mean, I haven't actually gone to take a look at the curve myself.
So it's not completely flat, but it's somewhat flat. So I guess these 12 models will get a reward, and that's not many others probably. But it's that because we really compare the models on a sample by sample basis. So for every sample in one of these two competitions, we assign one model as a winner. So we compare, let's say we have 800 samples, there will be 800 points to divide, and they are divided between the different models, just based on which model is best on that particular sample. And if you do that, you see that in the samples one column, you see that the top model wins 24% of the sample. The next one wins about 20% of the samples, and it goes down and down. So, and we think this is just a more fine-grained method to compare different models, and this is the way you can distribute rewards somewhat, not evenly, but in a fairer way, we think. And
I have to note we do have a power factor in there, so that if your percentage of wins is higher, you get even more. So that's also a factor.
Yeah. Yes, but you could imagine two models being good on performing well on different subjects, and both of these models have merit, and we want that to be reflected in the score that they get in the end. And what would even be better is that if two models would be good on two different subjects, that they would be merged into a model that is that performs well on both subjects. And we think merging is definitely an interesting method, and it can totally work and produce good models. But we do leave that up to the miners. So I'm not sure if they have discovered and explored that already, but I certainly hope they will. Another aspect of the collaborative part is that we write blog posts with insights on growing models. For example, you can grow Llama models in the hidden size dimension, but it's there are a few caveats and tricks that you have to look out for, and we try to describe that in blog posts to share the insights that we also discover ourselves during experiments with training models. And we also write some blog posts on incentive mechanisms to make sure that it's clear how we score all these models. Yeah. So what's the
you said that there is there's a fairness to the way in which you do loss comparisons that is different than, say, 9. I know 9 very well. I used to, or at least I used to. When you're evaluating winners in this competition, you said gold, silver, bronze have a less steep incentive landscape. What is it about the validation mechanism that creates that less steepness? Why does that show up in the way that you structure the rewarding?
Well, subnet 9 is just winner takes all, right? So if you have the most wins, you will get more or less all of the incentive. And they recently moved to just looking at the average loss of a model on the sample set. And by nature and by design, by design. They just assign one winner, and it's a way. It's something you can do, but we think this is fairer and also reflects, for example, that as I said before, that models can perform well in different domains, and you lose that information. So it's if you just assign one winner. So I think it's a little bit more a fine-grained comparison between different models.
And we do want to have a number 2 and a number 3, so everybody keeps competing. So you don't end up with Subnet 9 having a winner staying on top for a very long time, which is very nice for the winner, but everybody just stops competing. At least that was our experience in Subnet 9.
There is an aspect here to an epsilon. I think you guys were the first to discuss epsilon decay, to the point of maintaining competition, right? In one of your slides, you spoke about this, two things. There's the incentive mechanism. There's also the maintaining competition. So there is a decay on the epsilon. So just so people on the audience know, epsilon is it's a time-based boost to your loss when comparing against a peer that has committed a model after you. And this is there to stop people from being able to steal your model and simply resubmit it and get the same score. But the epsilon being static over a long period of time turned out to be too much of a hurdle to climb, especially when it was large and the models had reached a fairly low point of convergence. You guys came up with this idea of reducing the epsilon. How is that done? And how do you set that parameter in such a way to simulate competition?
Yeah, you want to take that?
Yeah, I'll tell. So we start with an advantage of 0.4%, and it halves roughly every week. So that means that if you upload a good model that is hard to improve on, you don't get infinite rewards. So at some point, so if your model is, say, only improvable by 0.1%, then somebody will upload a model that is better by 0.1%. That model is actually better than your model. So we thought it would only be logical that the better model would eventually win. And that's the main difference from having a static advantage. So eventually it will win, and that will be, if it's 0.1%, it will be after 2 weeks. And we figured that, well, it was basically based on our own experience in Subnet 6 and 9. We kind of just guessed these numbers, and it turned out to be we think just fine, where people still get the incentive and get the reward that feels fair for their work. But it does prevent models staying on top while not being the actual best model.
Right. It does feel to me that the parameter should be tuned maybe by the size of the model or the loss or the expectation of how much compute is required to improve upon it. But perhaps.
But for bigger models, it's also fair to have an advantage for a longer time, because it's really harder to train. But this advantage will decay to epsilon, really like a small number eventually. So the problem is, if you don't decay this advantage, at some point someone might have an improved model, but it would never be worthwhile to publish it. And in our subnet, it's always valuable to publish it, and you can even publish it and just wait. Eventually, it will be rewarded if it's better.
Yeah, so that's also a good point that it stimulates early uploads. And in the other case where you have the static advantage, it only stimulates to wait until you have that advantage. So an early upload is always worth the effort.
Yeah. So what's our next stop? And I think soon we are ready to increase the model parameter limit from currently it's 10.5 billion parameters. We can increase it to 20 billion parameters so that the llama can grow a bit. And yeah, we did a lot of work also last week where we, so that big models can be evaluated. We have the slice llama that works well, so that can load the model on the GPU in parts, in chunks. But we had one limiting factor that was still present, and that is that we loaded the whole model in CPU memory. And we solved that last week. So I think we can soon increase the parameter limit to 20 billion. And then we'll see what miners can come up with. Because I have to thank I didn't do that before, but I really want to thank all the miners who are active in our subnet, and they're a super important ingredient to make all this work. Of course, also the validators also perform useful work because these models do have to be ranked, but the miners have to be have the extra creative part where they have to come up with good tricks to produce great models. Yeah, and that's more or less what we wanted to discuss. So if there are any questions, we can try to.
Why not 1 trillion? What really is the bottom? It's actually it's a legitimate question. I mean, I think the question is more like, why not unbounded?
Well, there are all these validator limits that we have to think about. So storage is not infinite, and bandwidth is not infinite. So we want to move slowly and but steadily. So we really think that doing it in steps can be a useful feature. So in the near future we can increase it to 20 billion, and the next step could be 40. But I think that's more or less the steps we should try to take, and not an order of magnitude as in times 10. But I don't see a fundamental limit. It's just bandwidth and storage are somewhat tricky.
There's
and evaluation time, of course, because 1 trillion will take forever to evaluate.
Yeah.
It's good that you guys are pushing this and pushing this as much as you can. I know you're trying to keep it so your validators don't go offline as well, but the larger the space is that miners can explore into, going back to one of your first slides, you said, hey, what did you say? You said, can we do it? Here you go. Train smarter, not harder.
Yeah, exactly.
And the less limitations that you put onto the training script, the more you focus purely on the metrics, the more that miners can push into this and find novel ways of, no, someone will say, like, there's no way that we could train these 20 billion or 30 billion per models. No one has the compute. It's not enough incentive. We need more money. And then somebody does it, I believe that your team, as miners yourselves, were some of the first to crack the 14 billion model size in 9 and 29, and you did it by actually filling out the model from a smaller model. And some people didn't like that, right? They were like, no, that's cheating.
Yes.
Or it's not what we want. And I understand the perspective, but also I personally believe that this is exactly the type of thing that you would want to see, right? Where miners go and figure out a way of not doing any work at all, but still managing to lower the loss.
But I think if we put on the miner hats, that's what miners do, right? They are kind of lazy. They try to find the easiest way to gain incentive. So you have to make sure that your validation mechanism aligns with what you want to achieve. And I do think that large models, if they don't perform better than a smaller model, they bring no value. So I really think that yes, that's. I think if a small model performs better, it's just the best model, and we shouldn't even look at the bigger models then.
Do we see miners on this subnet and other subnets just stealing like a 7 billion, or a 14 billion that's from a Hugging Face from Meta or wherever, and minorly tweaking the model to perform well on the incentive landscape? Is that a meta?
That's a good strategy, I would say. If you find a model that's better than all the models that are there, you should definitely upload it and gain incentive. Why is that cheating? If it's a better model, it's a better model.
Yeah.
To play a bit of devil's advocate, do you think though that the value of the subnet eventually is the ability for miners to train models from scratch? And if you're allowing them to perform this type of behavior where they steal models from other places and lower the loss, that's not actually a reasonable skill that you're training miners on the subnet to perform, if that makes sense?
Now, I think the value of the subnet is to have a training machine. So it is just one big training machine with smart miners doing smart stuff. And as of now, we're just training these foundational models, pre-training basically. But as soon as this runs smoothly, which is approximately now, we just see how this works out with growing models still. But we can start doing other kinds of training, such as fine-tuning, which is basically also just training, which should be possible with this infrastructure.
When it comes to combining models, early days on 9 saw some metas around merging models. I don't know if that's the case anymore. In fact, like, you might have to pull up some miners from your subnet to know if that is indeed what's happening, or perhaps you guys would know. You've been growing models. You think that that's definitely a technique that works very well. You posted the paper in the chat. But merging, is that still a meta? Is that something that you can incentivize more of?
We encourage model merging because it's a way to combine the efforts of multiple GPUs into a better model. So we think it's good. So if people keep the same architecture, then it's very well possible that merging two models that are posted by somebody else results in an even better model. And we actually did that in Subnet 9, and it worked perfectly. And I don't see why that's a meta or why that would be bad. If it's a better model, it's a better model, and it should win.
You're purists, and I like that.
The code is the law.
The code is law, exactly. The data that's produced by the validators, which gives you this cache, this massive cache, could that be used as the base for a model merging technique?
Well, I don't think so. Well, maybe. I don't see exactly directly how. I think you have to kind of figure out the ancestry of the models that float around and see who could procreate with who to give a better model. But I'm not sure the losses are the thing to look at.
I've brought Cryptal Macrocosmos up on the stage to make the call more spicy. You guys know each other very well. You've mined their subnet, they've mined your subnet.
Oh, they have? I didn't know.
Well, maybe that's alpha. And where do you see the philosophical differences between these subnets at play, and like how can we evaluate which one is performing faster, if that makes sense?
Yeah.
Is there a way for us to know at a high level, okay, this incentive mechanism for training pre-training models, or this incentive mechanism for pre-training models is better?
Yeah, that's not an easy question.
Well, you could look at who's innovating faster.
Yeah, hi guys. Yeah, thank you, Jake,
Hi.
for. Yeah, sorry, I there's no hand to raise here, so sorry, I interrupted you. Go ahead.
Then
No,
take it
go
away.
ahead. I would be
sure.
happy to hear your views about it.
Yeah, sure. So thank you, Const, for inviting me here. So actually, I really like the idea of growing models, because growing models feel really like more efficient in terms of energy that you spend in training a model. But I see growing models interesting once you arrive or reach SOTA level on a given size. Otherwise, for instance, if you are training your 10 billion model, so if you decide now to grow it to 20 million, then you need to make sure it already reached its best potential on 10 billion before you grow it on 20 billion. So for me, the challenge is not how to grow first, but how to make the incentive mechanism fast enough or strong enough to push it to SOTA performance first, then you grow it at that time. But if you just like stop at a random point on the convergence curve and grow it, then you are slowing yourself down, because you will train on 20B what you would be able to train already in 10B. So the inflation in itself did not help in that sense. In SN9, the way we fix the
I'm not
size.
entirely sure this is true, but because you could also imagine that if you try to push out the last few percentage points from your model, you get large weights, for example, and you really put yourself in a corner where it's hard to get out from. So I'm not sure that this statement is true, that the only time to inflate the model is at the really end of the convergence of the training.
Yeah, fair enough. But actually, you can see it as a spectrum, because in the extreme case, if you say a bigger model is more interesting, so I will grow it early on. So in the extreme case, you grow it at the beginning, and here you know that this is not the way that it should be done, because if you just train it for, like, let's say 100 flops, like that is like extreme case, and then you grow it, you know that no, you still have potential to push it as possible in order to grow it. And in the paper that you also refer to, you see that they grow at the point where we start to see this kind of saturation on the loss curve, and is at that point.
But that's the choice of the miners. So the miners may decide when and how to spend their GPU effort. So they can decide whether it's smarter to grow the model and then train it, or to not grow it and train it first. I don't care. So these few extra bytes, they know, what does it matter? A few extra bytes on Hugging Face, a few extra bytes on a glass fiber, a few extra bytes or gigabytes, whatever, on a validator. It doesn't matter. It doesn't hurt anyone. If the loss is better, the model is better. And the bigger model is typically more compute intensive to train. So typically you want to have the smaller model until the point where the bigger model just performs better when training. So I don't see this philosophical thing where you have to stop training at some point and then grow, or who cares? Just train the best model you can train, however large it is.
Exactly.
Well, and then the question is, why not make it 1 trillion? Okay, because it has to be within reasonable limits, because it has to be possible to evaluate it, etc., etc. But I don't see the philosophical point you're trying to make.
Actually, the philosophy. So I agree on the point that we need to make it better. But as a subnet builder, this is like a new training environment. I'm also concerned about with any given size, like even now, if we grow to 20 billion, which is like has of course potential. I'm also concerned about, can we at this size, can we push to SOTA level? Like what's the potential really on Bittensor environment? Like, is the data set is enough? Like, is if we create the best training job on FineWeb, is the model will be good even at 20B? This is the philosophical question. Where is it going to converge? Until when? And that endpoint, is it interesting for in the SOTA point of view? So it's about also the quality of the training, not only because I can get the loss go down on any size actually, but I'm also interested until when, and is that interesting? Is that level interesting? Is the Bittensor network subnet is able to push it to a level that is interesting from a product or like research?
I think so. Well, I think if we don't believe that, it's, yeah, we have to believe that. I mean, that's where the value is. We need bigger models.
Exactly. We do need to be able to train big models, but we do need also to enable this big model to reach the level of its peers in state of the art. So
yeah, but I don't see the problem.
There's no problem actually, but the issue is also there are other aspects to look at. Is, for instance, epsilon. Like the epsilon was a very interesting idea, and also maybe the data set. This is what the direction we're going in Subnet 9. The data set is the kind of fundamental, and there are other design choices. There's the change of the data mix while you're training. There's the annealing, and there are many ideas that are fundamental in training a model. And maybe if we don't apply it, a 20B will end up performing as a 7B maybe, or less in state of the art. So this is kind of, I think there are ideas that should be kind of also combined, like size is important, but also there's many mechanisms in the subnet that also should be tested, and monitoring that should be tested to make sure we are going to an interesting target.
Yeah, I agree, but I do think that the loss value is the fair value to look at. If a bigger model can produce a lower loss on the FineWeb data set, it means it's a better model of that data set. It predicts the next token in a better way than the smaller model. And I think that's, it's just a starting point. That if you want to use the model in an application, you will have to fine-tune it. There's no doubt. Because you cannot just look at pre-trained model and pretend it's good at some other task. You have to fine-tune it. But I do believe that if a bigger model produces a lower loss, it has learned more features about the data set that it was presented. And in that sense, I think this is an objective measure of what it means to be a better model.
I slightly disagree on this point, because what you start, if you look at the dashboard, the perplexity benchmark on our dashboard, what you can see is that on FineWeb, actually, our model is beating, only on FineWeb, is beating comparable size state-of-the-art models. So actually, the risk with a bigger model, you will be able to overfit on FineWeb, so you will see your losses.
It's not overfitting. This is nonsense. But the other models are fine-tuned in different ways. A pre-trained model will not be able to answer multiple choice questions very well. It's just not. You have to present it some specific multiple choice questions first, and it's all in the fine-tuning. If you compare it to other models, they are fine-tuned for specific tasks. They're not just pre-trained models.
Exactly, but actually, the SOTA benchmark, you usually test your pre-trained base model on multiple choice questions, and also when it becomes an instruct model, you test it again. And here, what I'm talking is only about base models. So actually, eventually, if you don't look at the data sets, you will have a very big model that is trained only on FineWeb, and you will get a very low perplexity on FineWeb, but you will have a very bad perplexity on all other data sets. And this is what you can see on the dashboard. Like if you don't look at this, you will end up with a model that is that's not improving on all different domains that we see in state of the art. So you need to stop it at some point and make it also push toward other domains explicitly, like with an explicit mix of domains like reasoning, math.
Yeah,
Otherwise,
I mean, I do not disagree.
Let me jump in here. I think I agree. There's an interesting philosophical debate here at the core, and I think it comes down to if you set up the data set properly, the lowest loss on that data set is the best model that you can hope to achieve from that network. Is that something? And I actually, that's my intuition as well. You give it the right data set. You attempt to compress that data set as big as possible into the fewest number of parameters, or as many parameters as you like. But if you can compress it, you've done the job of understanding it. And so the myopic focus purely on loss, not forgetting everything about the road taken, the data set trained on in order to attain that loss, is in some sense the best way to go. And I'm not sure I understand your argument, Alan. Is it Alan? Correct, Alan?
Yeah, both.
Crypt Alan. And so, but one question I have for your team, R2H, right? So Macrocosmos has their dashboard right here on against a couple models. Why isn't there a dashboard 29 versus 29 versus 9? And would it even make sense? Is that an apples to apples comparison? How well are we performing on benchmarks?
Yeah, so for me, it doesn't really make sense to look at the multiple choice answers and benchmarks. So for us, indeed, it feels like the loss is objectively the best thing to look at. And if we want to look at these other benchmarks, we have to do some fine tuning of the model, some instruction tuning, whatever, to
that's not exactly
to
true.
make it more suitable.
Or is it? Is the point that that you're making right now that the performance on standardized benchmarks of pre-trained models is not something that we should care about? It seems to be your argument, right? But I was not under that impression. My understanding was that yes, the fine-tuned models will perform better on these benchmarks for sure. Obviously, they've been instruction fine-tuned to perform well on multiple choice questions, but a very good pre-trained model will do well on standardized benchmarks anyways, with few shot prompting.
I can believe that, but my guess would be that the variance that you get might be large, and in that sense, it's hard to compare models that might be close together in performance using such benchmarks. But
it's an indicator. If it's close, of course, you have a level of variance, but it's a very important indicator. If you have 10% on MMLU on a pre-trained model or 30%, this is a strong indicator. But yeah, if you have 30 and 30.05, then we don't care about this 0.5. Then we will fine tune and we will see who wins. But it's very important, and this is why we see it absolutely on all research paper. We evaluate a pre-trained model, and after it becomes an instruct or chat model, we evaluate them on the same benchmarks. There are some benchmarks we don't, but these multiple choice questions are used for both base and instruct models because they are important, and we can see the difference, the correlation actually. If you go to Llama 3 or DeepSeek or Qwen, and you check the performance before and after, you see that it's very correlated and it's very informative in indicating the final performance, the final instruct performance.
And a quick question as well regarding purely loss. I mean, your comment, RWH, that okay, so perhaps the benchmarks are not the right way to evaluate these models, but you are actually pre-training these models both in 9 and on 29 on the same data set. It's FineWeb, if I understand correctly.
Yeah.
And so why is there no way for us to get just the raw token loss out of this leaderboard? It seems almost like it needlessly complex, because it's difficult. I can't go to someone and say, hey, look, I've got this great model. I show them, this one's got 7,737.6 plus or minus 3,432. And they go, well, what the fuck does that mean?
Yeah. Well, we can certainly do that comparison. But the problem is that if you compare models, you have to compare them on the same samples. Because if you take a different sample set, the score will be different. The mean might be the mean, of course, is the same, but the variance of the loss you get is enormous. And there's also a slight detail, and that is that we don't pack the samples in our subnet. So that's also different. So in subnet 9, the samples are packed. So completely unrelated samples could be packed together in the same sequence of 4,096 tokens. And we don't do that. We only do full samples in our subnet.
This is sample packing. Actually, this is not something SN9 invented. This is done.
No. I'm not saying that.
Pre-training, and this is better for efficient training. Actually, you use
I agree.
The full length of your sequence.
Yeah,
but
I agree. It's better for training, but we don't see it as it's not better for evaluating in our belief anyway.
Yeah, the evaluation, it will be more relevant, of course, to evaluate. This is so the whole subject why we added to monitoring SOTA benchmarking also, because for us, actually, the evaluation perplexity with sample packing is not exactly to know how good we are on math. This is in order to compare with SOTA models, perplexity, to be able to indicate, did we reach our potential on FineWeb? So we take a SOTA model like DeepSeek with a comparable tokenizer size and comparable size, and we take our model, we compare their perplexities with sample packing on the same conditions exactly. And if we see that they have a similar perplexity level, this is an design indicator for us that now we think we're good on FineWeb. We think that SN9 is able to push on a huge data set like FineWeb. This is a really nice indicator. Then we are reassured now we can add more data sets, we can add code, mathematics, whatever. And we know that if we add them all, we will be able to also to push perplexities on all of them and potentially reach state of the art that way. So it's an indicator. So we need to know where we are going on perplexity, but performance and like reasoning abilities, we use it on SOTA benchmark as done in academia. So this is kind of the philosophical idea behind it.
Yeah, okay.
Great. It's scintillating PhD duel. Thanks for letting me make the conversation incredibly spicy, guys. This is fun. We should have done this at Neural IPA with knives.
You know what? Let me say one thing. So what works in a subnet to have competition and gold and silver medals, I think it works for subnets as well, right? I think the competition helps us both to perform better.
So on that point, can we have a way to objectively measure the models from 29 and 9? Like, how do we do that? Because just like in a subnet, the metric of validation is super important. The fact that we can't measure it on 29 in apples to apples comparisons to 9 seems problematic. I'm curious also just to know if there are models on 9 that are on 29 and vice versa, and into which direction they are moving, and
Yeah,
Well,
one point on the silver medal, I do think this is an interesting idea, and I'm interested about the dynamics that are happening there. So this is really interesting experiments you're doing, and I like this idea. And this is experimental, so we see if it works or not. But this is the best way I think to do it, is to try it. About the comparison, so SOTA benchmarking will be interesting, but there's something that we need to take into account, of course, the model size, but also the initial point. So I know in your C01 competition, you initially started from phi, which is an instruct model. So it's not, you confirm this, but it's not starting from the scratch. So it already has no in it. But yeah, you can maybe better explain this point. But my point is, in order
we uploaded it
to check these parameters.
Sorry.
Yeah, go ahead. Sorry.
Yeah, so we originally uploaded a phi model, for Microsoft, and miners improved it on the FineWeb data set. So it's different now, and also it at some point one of the miners grew it from 3.6 to 5.6 billion parameters, I think. And then we recently grew it from 5.6 to 9.8, I believe. And then the other miners took over quickly and made it better. And again, on the FineWeb dataset. But it's totally possible to compare apples to apples in the Llama competition models from Subnet 9 and Subnet 29.
Yeah, the 0, right?
Yeah, exactly.
No, the packing is different.
There, of course,
it's not possible.
Yeah, so we can compare it, but we will have to do either form of packing, and we can evaluate it with both forms of packing.
Compare unpacked, please.
Yes, I agree.
I made it. I'm finally here. Sorry about this, guys.
Hey,
Hi.
Trying for a while. Rolls from Macrocosmos. Roll. Is it Roll? Roel?
Yeah, roll is fine.
And you've had a fair amount to say in the chat so far. And here you're up on stage. You work for Macrocosmos, and do you work on the Subnet 9 team as well?
Exactly. Yeah, pre-training and sometimes also fine-tuning, but mostly pre-training.
Cool. And welcome to the stage.
Yeah, thank you, man. Massive respect to the guys at Coldint. Also, they're crazy good miners, and it's been a lot of fun playing the subnet owner versus miner game with you guys. So massive intellect respect on that side. A question that I've wanted to ask you guys is, especially now that you're trying to grow model size, like we've seen across the history of your subnet that sometimes you step in to keep the competition alive, which stagnating competitions is something that you guys have both suffered and enjoyed at Subnet 9, so it is a known problem. We have dealt with it in different ways. But I would like to hear like your opinion also, if someone else wants to jump in, Const. Do you think subnet owners should have a more active role in this? Like it's definitely a fair strategy, but it feels like to me it feels like a bit of a incentive weakness if you have to jump in and declog it yourself. And I mean it again, like with intellectual respect, it's just a strategy that somehow it doesn't feel as elegant as it could be.
Well, I think it depends on the subnet. So I think in both our subnets, the rules are clear. And as long as you don't start working on a model before you announce that the competition will change or something, I think it should not at least be forbidden or frowned upon if you mine in your own subnet. We don't do it very often, and as you say, we mostly do it to if the competition stagnates. So this was, of course, at the start of the subnet when we seeded the subnet with a few models, and at some point in the phi competition we grew a model. But I think it should be allowed.
RWH, you have to add that we also did a lot of work publishing articles and explaining more about how to grow stuff, how to train. And then if these miners don't pick it up, it's too bad. But then I think we step in and grow a model, and then the miners take that model. Because apparently growing a model is hard or something, I don't know. I try to explain it the best I can, but okay, apparently we have to do it. Then we do it. Who cares?
Yeah,
Yeah,
we
I agree
definitely
that
don't try to benefit from changing rules or anything. So.
What do you think, Const?
Sorry, I was muted. I think that if the game is well defined and is not easy to exploit, then a subnet owner can jump in. I think that if there are obvious problems or quite big question marks with the incentive landscape, where people might wonder if the design is favoring the subnet owner, then I think it becomes quite problematic. Especially if you're constantly developing and improving or changing the incentive landscape, you can't mine your own subnet because you would have privileged information about how it's changing over time, and that would allow you to beat out other miners, and that just undermines the competition. I do think though that the role of a subnet owner should be about educating their miners and making the game fair and firm before mining, and in some sense, like if you can mine your subnet, perhaps there's just information that you should be giving out to your miners, both in documentation, etc., in order for them to do the job, rather than you having to focus your attention there.
Okay.
So then I have to repeat indeed what Mew said. So we have been writing articles about how to grow models and where the tricky bits are, and So then, if we increase the parameter limit, we hope that the miners find these articles again.
Okay. And now recently, the last time you published that, you might jump in again to bring back the competition a bit to life. Was the warning of you about to do it enough, or did you end up submitting one? I don't remember that part of your leaderboard.
In Phi, we submitted one, but it was when it grew from we grew it from 5.6 to 9.8, I think. But it was it was on top for a very short time. The miners picked up quickly after that, and I have to say, I think even if I try, I can't beat the miners anymore. They have produced pretty good models.
Okay, thank you. I think that's a good sign as well. Thank you, guys.
Yeah, absolutely. But it's also a sign that we might have to move to a bigger model size. So at some point, the loss will saturate, of course.
1 trillion. I have a limit. I can't wait for that moment. RWH. Mew, thanks for coming to the stage. Roel, Alan, I appreciate the debate that we got going. But we'll end the call here. Yeah, thanks for being up on stage. It was a great presentation. Thanks for having slides, Coldint. Looking forward to seeing these models head to head, apples to apples, and being able to evaluate the two subnets and on the same playing field. But really interesting, technical innovations that you guys have done, from pipelining so that we can go to 20 billion and above. It sounds like 20 billion is actually not even the limit to what we can do. I hope that we can do that as soon as possible and have the largest decentralized training run in some sense in the world. And yeah, looking forward to talking to you guys again on stage sometime in the future. Thanks for coming.
Great. Thanks for having us.
Thanks for having us.
Thank you.
Ciao, everyone. Take care. Have a good night.
Cheers.